college entrance exam company determined that a score of 25 on the mathematics portion of the exam suggests that a student is ready for college-level mathematics. To achieve this goal, the company recommends that students take core curriculum of math courses in high school. Suppose a random sample of 200 students who completed this set of courses results in a mean math score of 25.4 on the college entrance exam with a standard deviation of 3.1. Do the results suggest that students who complete the core curriculum are ready for college-level mathematics? That is, are they scoring about 25 on the math portion of the exam? It completes parts A through D below. So part A, state the appropriate null and alternative hypotheses. The appropriate null alternative hypotheses are HO is the population mean, so mu is population, X bar is sample. Occasionally in our book we'll use a big capital M for sample. So population mean equals (25). And it may have been easier to run over here to the H1 or HA first. So again, H1 is mu is, and we want it to be greater than, right? 25. Now, a quick note here on the null hypothesis. So again, it may have been easier to go over here to H1 first and say, okay, we're looking for something, we want this to be scoring above 25. And then you come over here, and in some context, we will say the exact opposite of greater than, which would actually be less than or equal to. And I would give you full credit for that. And so if you do that on this, I can override these scores easily. For many of these problems, they want you to put the equals. So in general, if you see the symbols, you're going to just use the equals for HO. And if you see the words on out there, you're going to end up using less than or equal to or greater than or equal to. Okay, now recall that on many of these tests that we end up running, there are some assumptions. Sample size is larger than 30. Students' test scores are independent of one another. And it says they were randomly sampled. Suppose a random sample. And we have to assume independence of one another. That is that, you know, we don't have a brother and sister that are possibly, you know, together in the same household, or a set of twins, things like that. Okay, use the p-value approach, and alpha is 0.10. So this is sort of our cutoff value to test the hypothesis in part A. So let's identify the test statistic. I'm going to run over to StatCrunch. Okay, so we're going to go to Stat, T-Stat, and we're still looking at one sample, but this time we just have a summary of the data, where I'm given a sample mean, I'm given the standard deviation, and so on. So we see the sample mean was 25.4, and standard deviation is 3.1, and N was 200. Okay, and we're performing the hypothesis test where this was 25, and we were hoping to be greater than 25, and press compute. Okay, so here are our results. We got the sample mean 25.4. Test statistic is 1.825, and the p-value 0.0348. So we're running just to two places, so it's 1.82. Again, and if you put 1.825 there, I'm not going to count that wrong. So just let me know, and I can override that. Particularly on these multi-part problems, you don't want to have to do all that again, just for a rounding error. And then the p-value round to three places. And our p-value 0.035 to three places. And there we go. So write the conclusion based on the results. Okay, so this is a relatively low p-value. Now how low is too low? We compare it to alpha. 0.035 is lower than 0.10, so we're going to reject HO. So reject the null hypothesis that there is sufficient evidence to conclude the population mean is indeed greater than 25. Okay, I'm kind of looking up here to my research hypothesis. We're going to reject HO, so we have to sort of embrace our H1 or HA, our research hypothesis. Okay, well, I hope that